Hey, welcome. Step 41 of the Supernatural code walkthrough. This one is going to be a little different. Basically, we've added a number of new enemies. A ghost skeleton, the Wolfman, the Eye. And most of this code change is describing the behavior of these enemies. There are a number of other changes that aren't really significant, so I'm gonna skip those because I don't know how long it will take to go through all the behavior video, all the behavior code. Now we're gonna do a number of enemies, and as you can see, the ghost skeleton only has a few animations, so that is simple. The jumping toad is a little bit more. That's another enemy. Is going to be a little bit more time consuming, but once we see what's going on or trying to do, the other ones will hopefully be fairly simple. I think the best thing to do though is to just play the game first and see what the enemies do, see what their behavior actually is, and then we can look at the code to see how we do that. Now I think I've turned the music on or off. I think I've turned the music off. There we go. Yeah. So that's part of the code change. There's been a define introduced that will either compile or not compile the code that calls the music player. So that's just for testing purposes, not to have the music all the time. So I'm gonna go with player Sam because Sam at this point is totally overpowered, and we're gonna use Sam because it's just easier. Okay, this is the Wolfman. Now the Wolfman, as you can see, he walks left and right. He toggles his direction if he's blocked, and he does random jumps. Now I'm thinking that the randomizing of the jumps and testing whether or not he's going to jump isn't really working as we would like to, because I can let him walk around, and he jumped once, but after that he never jumped again. But we'll take a few shots at him. So we've heard him again. I've heard him twice now. Now we'll see in the code later that the probability of him jumping now should have increased. But I think the randomization isn't strong enough to let that happen, or the odds are just not in favor of him ever jumping. So this is a bit of a lame enemy now. I'll just destroy him. Bang, there he goes. Being Sam at this point, this is great because I have unlimited range. Oh, and I can hold enemies. All I have to do is keep the fire button pressed, and the job is done. So, and this makes it very easy. So these Wolfmen are now just going to walk around. We've seen them jump, right? But for some reason, two of them have coincided with two others, and they seem the same, but this code isn't complete. So I just gave one a couple of shots. I held them. So it's not good, but something works. I have to destroy all of them. And I may have picked a pattern here that wasn't too smart. Let's see if I can at least destroy one. Boom. 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 Oop. I don't want to die. Oh well. Okay, and there one. That's the last one. Okay. So that's the Wolfman. Now we get the ghost skeleton. As you can see, the ghost skeleton doesn't move. He just animates. So there's a big difference in the code between animation and moving. And then there is also a big difference between walking movement and just moving left and right. So I'm just gonna kill these guys. They amount to nothing. So these aren't enemies yet. They're just annoyances. Bullet has no function when I'm oh, these are the toads. They are already annoying as they are. As you can see, they jump, and when they jump, they go left and right. And when they hit a wall, they toggle their direction. That is important. So they also don't move left and right. They don't walk left and right. They just jump, and during their jump, they take a direction. They go in the direction that they were going, and they toggle when they hit something. I'm just going to take that for points. There's no need, but, you know, and that one. Okay, then this is the eye enemy. As you can see, it only moves diagonally. It doesn't walk. And the animation is that it opens and closes, and it holds position while it does that. But the enemy is vulnerable at all times. So I can just shoot one while it's closed or open. That doesn't really matter. I would probably say, okay, this enemy should be vulnerable only when the eye is... oh, shit. Tried to take that. Only when the eye is open. It would make it slightly more interesting. And I would limit Sam's range, I guess, because this is just too powerful. This is an older level, so we've returned, I think, to an older. So we've seen all the new enemies. We've seen the ghost skeleton. We've seen the eye. We've seen the Wolfman. So you get the drift. Right. So let's look at the code. Basically, each of these enemies is a state machine that we're trying to describe. There are several ways of doing that. The way that is, just as a warning, the way that it's used here results in spaghetti code. It's a lot of jumping around, a lot of testing. Are we jumping? Are we falling? That kind of thing. We have an element of animation that we have to do, but we also have to have some movement of the sprite. It's complicated, and I'm going to do my best to explain it, but I will probably at some point be scratching my head and thinking, what the hell is going on here? So, but that's just the nature of how this is done. Anyway, the ghost skeleton. Let's look at the ghost skeleton again. That's this guy. Basically, it just has three animations. The skeleton. We'll have a look at its animation table, which is here. Skeleton animation table, as you can see, has 4 entries. Skeleton 1, 2, 3, and 2. And then it'll go back to 1, 2, 3, 2, 1, 2, 3, 2, and so on and so on. So how is that done? Back to the find all references. Go here. How's that done? We delay our animation using the generic delay counter. We end it with 3 so that we're sure that we only wait 4 frames. If that's not 0, then we have no animation update, and otherwise we just increase our current animation, we load it, we end it with 3 so that we are sure that it's only 0, 1, 2, or 3. And remember, there were 4 entries there. It's just one looping back. and then we store that back into the animation position. And to get the correct sprite pointer value, we go to that animation table, because the sprite animation position only holds an index into this little table. And then we take that sprite shape and we put it into the sprite pointer base. The sprite pointer base being the 8 bytes at the end of display memory, where the VIC finds the pointers to the sprite shapes. Right? This is all programmer's reference guide stuff. Now, I'm going to skip the jumping toad. We'll do that in a minute. I want to go to the wolf. Y 4433. I have a little state machine drawing made of that, which I will show here. So this is the Wolfman. And in this little schematic that I had ChatGPT make, not sure that was the best idea, but you can tell that either the Wolfman is grounded, he is walking right or walking left. Where's my cursor here? Walking left. It can go from idle to walking left or walking right. It can also go to jumping at the end of if it's at the end of a platform, it can jump, or you can also just randomly start jumping. From jumping, it can also go to falling, but it can also be walking. It could also be walking left or right and then go falling, but that's not in this. That is not in this schematic, but that's not correct. And of course, if we're blocked in either left or right direction, then we have to turn our direction around. So that's basically what we're trying to describe. So the complete behavior in a picture would be this, and then we have to make that into code. So the one thing that the state diagram doesn't show is the hit back. Hit back is when we hit an enemy, it sort of jumps back a little bit before continuing on what it was doing. So we first check if we are hit back at all. If we're not hit back, we exit. Otherwise, we decrease our hit back count. We load a direction. If it's right, then we go object moving left blocking, or right is object moving right blocking, which also takes into account if we're backed into a wall, then we bounce back, or we just stop moving actually. So that's the hit back done. There's no hit back. We have to animate the wolf. First, we look at its jump position. If we are in the middle of a jump, then this jump position will have a value. It's an index into the jump position table is a number of sprites that describes our jump. So this many pixels per jump, per frame that we have to be moving in a jump. And that number decreases so that our jump is first large and it tapers off until it's 0. And then we stop jumping and then gravity takes over. Anyway, so we load this jump position. If it's not equal to 0, then we say there's no animation update because there's only one animation sprite for the jumping wolf. Otherwise, we are walking and we need to do a sprite delay. Do we do that every frame? No, we wait 4 frames. So we increase the animation delay, we load it. Have we reached 4 yet? If not, then we're done animating for now. Otherwise, we do an animation. We first reset the animation delay so that we can wait a couple of frames for the next series. We increase the animation position, then we load it. We check if it's not larger than the number of animations that we have, just to make sure that we keep in our little loop, which is 0 to 4. Again, this animation table has 4, just like the ghost skeleton did. Now we look at the direction. And here's where the trouble begins, because now all of a sudden we have our left sprites in one end of the. I'll have a little look. These are our left going sprites. This is the jumping one. Then there's a right going sprite here for the jumping, and then the right walking sprites are all the way over here. So there's a difference of this to get from the left walking to the right walking ones. That's a problem. Now, this is an error. This facing left should be facing right, because if we load our sprite direction and it equals 0, 0 means walking right. That's the same in the whole game. That the fact that this label says facing left is just wrong. So if we're facing right, then we take our animation table value, and we've not seen it maybe, but if we look at it, it points to all the left ones, L1, 2, 3, 2, 1, just like the ghost, but it's the left ones. But we need the right ones. So we go back to this code. Where were we? I've lost my. No, this is spider. Wolf. Here we go. So we load the direction. If it's 0, it's right. So we end up here. We load this value, and we get the left animation frame. Now we have to add a number. What number do we have to add? The difference between right 1 and L1. So we have to clear the carry and add that number. That's unfortunate, because adding is a costly operation, and we have to do this almost every frame. This is not smart. For the left, we have to do nothing, because we just have the left one, and it's correct immediately. We load that into the sprite pointer base, and we're done. So this is the reason why you have to organize your sprites correctly, because now we get this. I think there is, in the sprite editor, is a move to index. See that? I think he could have done that. I think he could have just spent some time moving the sprites from one location to another to reorganize them the way they are displayed here, and to do, because that is basically for all the left and right. This enemy that we haven't seen yet, this is alternated left and right. I think Georg did this himself. And this is Sam, and this is Dean. But then this Wolfman is split. Anyway, let's just move on. No animation update. Again, either there is no animation, or we've done all the animating that we need to do. Let's continue. We have to start moving our sprite. Again, this is the downside of writing as a state machine this way. We have to check again. Are we jumping? If it's not equal, then we are jumping, and we do not have to handle any falling. Okay, so that's what we're doing. If we're falling, we have to update our sprite fall. Update sprite fall is the same for any sprite. It has one of those tables with pixels, a number of pixels in them, and they start with a small number, and they get larger. So each frame lets you fall a a larger number of pixels until you fall somewhere. Sprite falling. This also detects if we're done falling, right? So sprite falling is the result of update sprite fall. If it is not equal, then we continue to is falling, which is here. If we're done falling, then we're grounded. Remember the state machine? All of a sudden now we're grounded. We've reached that. So we're now not jumping, we're not falling. So we generate that random number. We AND it with 15. So the highest 4 bits, like the most significant 4 bits, are made 0. And the lower ones, they are left intact, like whatever random number this is. Then we do the compare. Remember, we had this little compare diagram. We do a compare. So we have this this random number in the accumulator. We subtract 15. Like we have the random number in the accumulator. We compare it with our annoyance level, sprite annoyed. So we subtract that. If it's positive, if the result of that is positive, then we continue on to is falling. Otherwise, we do jumping. That's how that works. We've seen, however, that this doesn't seem to work. So for some reason, we're always getting a positive result here. So let's see. I'm gonna put a little breakpoint there, and we're gonna see if the Wolfman ever decides to jump. Oh, yeah. Here we go. We set the Sam. He jumped there because he came off the end of the platform. That's also in the object walk left or right code. But as you can see, we never reach that code. So we annoy him a little. We annoy him a little bit more. That code is never reached. I don't know if we... I think if I hit him again, he just destructs. No, he's now more annoyed. See that it never happens. No, he's dead. So perhaps... Oh, wait a minute. Now we have 4 of them. Let's just... It does the jump, but only at the end of the platform. It never works. He's annoyed. Oh, I got myself killed. Yeah, but you can already see I can play this until the end of time, but these guys are never gonna... Now maybe, just maybe, if we said compare with sprite annoyed and we just add something. Well, because I can't, this sprite annoyed is always lower than whatever random number is generated here. If I said branch minus here, then it would be jumping all of the time. We can have a look at that. See if that... Do I still have my... Well, I don't actually need my... we can just see it jump all the time, I suppose. Yeah, there we go. Jump, 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 jump. It does nothing but jump. So I think we have the cause of a little. It doesn't matter. You get the gist. We have to have some sort of mechanism in place to handle that. Like, are we jumping? Yes or no? Are we at the end of our fall? Yes or no? And then do we initiate another jump? Right. So again, we take our sprite annoyed value, we add 2 to it, and then we store that in parameter 6. Now, what's happening here? You can see here that it decreases parameter 6, and then when it's 0, we say move done. So this means that we're going to loop this move step. It's a jump move step here. So we're going to be looping this for the number of times that we're annoyed, plus 2 for some reason, some magic number. And we're going to move in a direction. We're going to move left or right. This says that the more annoyed we are, the faster we move. That's really what's going on here. So let's have a look at it. So we decrease the parameter 6. If it's 0, then move is done. If it's not 0, well, then we look at the direction. See, branch equals 0. We move right. So that is supposed to be right. Move right is this code. We only move right if we're not... Look, we're looking at this. Are we jumping or are we falling? If either of those are true, then this has a value and we go to only move right. Object move right blocking. So this is moving right while jumping or falling. And if we're blocked, we toggle direction and we go back to move step. Move step was up here, remember? So move right means if we're jumping or falling, we just move right. And otherwise we walk or jump right. So the walking includes jumping off a platform at the end. And if we're blocked, we toggle direction. The toggle direction code is here. It's very simple. We take the direction, we exclusive OR it with 1, and then we store the direction back, which basically means flipping the bit, and we move back to move step. The same goes for going left. You say move right, no, then move left is the same code here. Are we jumping or falling? Then we only move left. Otherwise, we walk or jump left with the toggle direction and the move step. So that is kind of, except that we never jump. And so you might be thinking, hey, but we've already checked that we're jumping or falling. Yes, but that's for the animation. So checking whether we're jumping or falling, we have to do double also for the actual movement, right? So, but that's all of the code for the wolf. So now let's have a look at our brother Toad. I'm gonna go back to my notes here. The Toad is a little bit more behavior jumping Toad. Let's see. Oh, enter. Oh, there we go. It's a little bit more intricate because of the it can sit. Let's look at the animations. It does this is the normal state. It squats and then it jumps. And during this jump, it can move left or right. And then when it lands, it does this, and then it waits until it does this again, and it takes another jump. But while it's this, it doesn't walk left or right. And while in the air, it has to move left or right, and it has to change direction when it's blocked by something. So here's the same thing. We don't have any left or right frames. Like we're always facing head on. We do the hit back again. If there's no hit back, we just go out here, and the code is the same. We decrease the hit back counter. We load it. If it's 0, then we hit back. Oh, the direction. We decrease the hit back. That's funny. We decrease the hit back counter. Oh, of course. Yeah. Yeah, this is you get hit back for a number of frames. So do we do that? Yes or no? This is no. This is yes. We decrease it. We look at the direction. If we're going right, then we're going hit back right. And otherwise, you go hit back left, and we jump out of the function. If there's no hit back, then we do this. We look at a state. If it's equal to 0, then we're not ducking, which means ducking means we're at this state. Sprite state increases, apparently, when we are ducking. But if we're not ducking, then we continue here. But now we are ducking. So we increase our animation delay because we don't want to duck too fast. If we've waited for 6 frames, then no, we're still ducking, so we jumped out. Otherwise, we zero out our animation delay. We load our animation position. We increase it. We get our sprite shape. We store it in the sprite pointer base. Then we look at, have we reached sprite jumping Toad 1? So what we're doing is we're here, we go here, we go here, we increase it one more time, we're here. So compared to sprite, yes, if we are not there, then we are still ducking, we go out. Otherwise, we say, okay, start our jump, our sprite state goes to 0, so that the next time we reach here, sprite state 0, we're not ducking, no, we're jumping. And then we increase our sprite jump position here. So now we're not ducking anymore. We are jumping. Jumping is not ducking. This is typical for state machine stuff. What is the name of the state? The state's name is not ducking. No, it's jumping. So we load our current jump position. If it is equal to 0, then we start falling. Now, we've just begun our jump, but we may have jumped right into something above our heads that we can't jump through. Anyway, if we're at the end of the jump, then we're going to see if falling, if possible. Otherwise, we are jumping. So we look at our jump position. We look at our jump table size, because this is not the generic jump table, but Toad has its own jump table, which is like 12 long. So it has a different jump characteristic than we do, or the Wolfman does, or all the other enemies. Toad has its own jump table. If we're not at the end yet of that table, then we jump on. Otherwise, our jump is blocked. We mean by that, jump to jump blocked means we're ready with jumping for whatever reason. Otherwise, we jump on. So we look at our jump position, we increase it, check in the table, hey, which jump table entry are we on? How many pixels are we jumping? If we're not at the end there, then we just keep jumping. Otherwise, we do the Toad move. Have we had keep jumping yet? Oh yeah, keep jumping is here. This is, again, we store that value that we just loaded into parameter 5, because remember, we have to do a number of iterations of the number of pixels that we have to move. object move up, blocking. We check, we move the object up. We see, is there anything above us, yes or no? It returns a value in the accumulator, and it influences the flags. So if it's 0, then hey, our jump is blocked and we can no longer continue. Otherwise, we just decrease. We do jump continue, which is here. If it's 0, otherwise we start to move the toad. Moving the toad in this case means we have to move it left or right as well. So is our jump blocked? Then we have to set our sprite jump position to 0. So that we're either at the end of our jump. We jump to toad move. All of this ends in toad move, but we have to make sure that we do everything correctly. Can jump is from here. Oh, fall if possible. We haven't done that. So fall if possible. We update the sprite fall. That also returns a value. Are we blocked? Yes or no. If it is equal to 0, then we can start jumping because we're grounded again. This is going back to state ground. Otherwise, go to toad move, blah, blah. Can jump means we increase our sprite state. We set the animation and the sprite animation position, so the animation delay and the position to 0. We set our sprite shape to sprite jumping toad 2, that is that one, like the normal one. And we set that to the sprite pointer base, and we end so that the next time we go in here, we can start jumping. Now, while jumping, we have to look at our direction because we're going to have to move the toad left or right. If it's equal to 0, then we move right. Again, move right. Blocking, we can jump into something and change direction. If we have been blocked by something, we return 0 here and we toggle the direction just the same way. And the left code is the same. I said it was going to be complicated, and it is complicated. But once you walk through it a couple of times and look at it, you kind of sort of can find what the structure is. I think I would prefer the code to be more state oriented. Just is it which state are we in? Are we this state, then do this code? Are we that state, then do that code? That may result in more redundant code. I don't really know yet, but this is hard to analyze and therefore also hard to debug. Like the ghost skeleton is really simple, right? It uses the generic counter to record the delay. If we haven't had the amount of frames yet, then we don't do an animation update, and we're immediately done because we're not moving. And otherwise, we increase our position, we load it, we make sure, we clamp it to 4, and then we load that back. And then using that position, we go into the Ghost Skeleton animation table, we get the right sprite pointer and load that, and then that's done. So that's how simple, how basic the animation is. So that is it for this episode. Again, there are some other things that I thought weren't too interesting. There is one thing though, that this clump of data, look, it's been moved. It's been moved right into it's been moved a couple of times. It's been moved to a place like 2000 hex. Place the data at a valid bitmap position. This avoids having to copy the data. This goes to a whole different subject of where the VIC sees this kind of data. And loading it there straight away means that you don't have to copy it. And usually what games do when you start up, they unpack themselves. That always takes time. But then sprite data being copied to the right place, character data being copied. So this bitmap data already being in the right place just saves time. I'm not sure if it's going to stay this way, but that's the kind of thing. Of course, new levels were added, but you've seen them, and we've seen that a number of times already. So I think we're going to leave it there. I don't know how long I've been talking, but that's it for step number 41. I'm going to go on holiday for a couple of weeks, so you're going to have to wait for the next, for part 43. But I hope to see you then. So bye-bye. See you later. Bye.